Let's see. So, yeah, good afternoon, everybody. Yesterday in the first lecture, we made it just to the point where I was able to introduce the standard model. And in a way, I behaved like the German railway system of building up already a delay. And now I have just to continue with another delay, but I try to make up for it. So to complete actually the mission of the first lecture, I wanted to give you at least a little bit of a round trip to some selected precision experiments that were milestones in establishing really the electric part of the standard model. So let me just go through this actually incomplete list, but it contains the, I would say, the most important players in the early phase when physics of the gauge bosons was addressed experimentally. So I think everything starts already with a experiment which is not exactly a scattering experiment, namely muon decay. You heard about this already several times in the context of, for example, Fermi theory. We have this kind of 4 fermions taking part in this reaction. Muon decays to an electron plus 2 neutrinos of specific type. And by measuring it, basically meaning measuring the lifetime of the muon, of course, you get a constraint. That means with the input parameter of the standard model, you can predict the lifetime. Typically, it's quoted in terms of the Fermi constant. And so you can really make contact between theory and experiment. And nowadays, it's mainly exploited in such a way that in this basic relation here, this is only a lowest order relation, giving you the relation between the measured Fermi constant and the rest of the input of the standard model. Typically, this relation is exploited in the direction that one solves this equation, including, I will talk about this later more, including radiative corrections. One solves this for the W boson mass. So when anybody is just talking about confronting the measurement of the W boson mass with, let's say, a theory prediction, it comes from muon decay. And this is really something essential and got some, of course, renewed interest last year with this controversial CDF measurement. So the first scattering experiment that really directly went to the heart of the gauge bosons with high precision was set production at lab, A plus and minus, to any kind of fermion antifermion pair with either photon and or Z exchange in between. And there was just a bunch of precision observables coming with these investigations, like, for example, measuring the Z boson mass, which is typically taken as an input for the standard model, the width of the set, the P cross section for this resonance reaction, I will come to this later, and various asymmetries. And there was a lot of knowledge that could be gained just from analyzing these observables. Next step at lab, sometimes called lab 2, was the run phase around 200 GeV or so, where here actually you set at the set pole about, let's say, in the vicinity of 90 GeV in center of mass energy. So in this second step, it was possible to produce W boson pairs. You see the major diagrams here again. And by investigating W boson pairs, of course, first of all, you could measure the W boson mass with higher precision, but also investigate these non-abelian couplings between the gauge bosons. And I will show you results of that later. It was even possible to have a little bit of information about quartic gauge boson couplings when an additional photon was just demanded in the experimental signature here. So moving on, we are here already entering the time where hadron colliders took over the lead in precision physics, first Tevatron, meanwhile the LHC. And there, of course, also single W boson and Z production is among the most important processes. Again, you can measure with very high precision, even higher than at lab, the W boson mass. You can also analyze, for example, the W boson gamma coupling when you have additional gamma radiation from here, for example. And for Z boson exchange, again, you can measure appropriate asymmetries. I will come to this much later, and transform this information into a statement on the so-called effective weak mixing angle. Going back to the picture for lab, Yeah, these asymmetries were basically also translated into the so-called pseudo-observables that we call effective mixing. More about this later. So this means hadron collider physics can also deliver information completing or complementing the one from lab in older times. What is also essential as input quantity in electroweak physics is a top quark mass, which is typically measured in TD bar production as indicated here, for example, for PP and PP bar collisions. I will not talk about this because the physics of this process is majorly driven by QCD, which is not actually my mission here to do. And just as an appetizer for the very last lecture, tomorrow in the afternoon, I will then also address completely new type of electric processes like vector boson scattering, where you have, for example, here W bosons radiated off, quarks coming from the proton and then scattering off each other, which is meanwhile measured at the LHC with quite good precision, which was not possible before. So it's a question of taste to include this already in an electric precision physics program, but it's at the very heart of electroweak interaction, so it would be not appropriate to omit this. Okay, more about this tomorrow. Let's view into those processes that I have encountered here that played a role before actually the LHC kind of took over the lead in our field. That means basically from day on of the Higgs discovery. Sorry, that was a bit quick. So let's jump into, for example, lab physics, where, for example, in phase 1, the C boson was analyzed with very high precision, and the observable one should start with is actually the cross section here, as a function of the scattering energy. And if you are near the C boson mass, it is clear that you basically see the energy depends of the propagator emerging. I hope you remember how it looked like. Every propagator, let's say, for example, for the C boson here, has a structure independent of spin, has a structure 1 over k squared minus m squared. And k squared is the square of the form momentum running through the propagator. So this means here the k squared is just the scattering energy squared, the Mandelstam variable s. And so we have a 1 over s minus m squared. It is squared because I have to square the matrix element. And if you just blindly do this, you get infinity if you hit the pole here. So something else must be going on. It means that the way you do field theory maybe is not organized in the most appropriate way here, which is in fact the case, because perturbation theory, as we do it, takes as a lowest order, at the, let's say, the very 0th order, the free propagation. And if you have just free propagation, it would mean that E plus E minus would just live forever, or the C boson would live forever, which is not the case. It decays, and the decay is exactly what kind of truncates this behavior that you run into pole, which is infinity. So I will talk about this also, I think, tomorrow in more detail to make this story short. At this very moment, if you do then some kind of proper resummation of higher order corrections already, what you end up with is the introduction of something that looks like the damping part in a Breit-Wigner resonance structure that you know already from mechanics. So this is a typical way how relativistically a resonance shows up in a cross-section. Okay, more about this tomorrow, but you see that you can just get information about the width by changing S, meaning the scattering energy, and just sweeping over this resonance shape. And you see the result here, actually. You even see different versions. In particular, you see here that radiative corrections matter a lot. For example, if you have something like Bremsstrahlung, where a photon is emitted from the incoming E plus or E minus, it reduces the scattering energy, and we will come to this also in more detail. It changes actually the dynamics a lot, which is not included in the simple formula, but if you include those effects, it will distort this shape. You see the effect here. there are two versions. Sigma from fit means it's just, well, a prediction out of the box, so to say, with this radiation, for example, included. And this is not exactly the shape from here, but what you can do, you can try at least to unfold, as the experimentalists say, or to kind of kind of strip this emission pattern away to go really to the heart of the process here without radiation. And this is here actually called QED unfolded, which is a result of a prediction that ignores photon radiation, and you see it has a similar shape, but it's significantly quantitatively different. You can, for example, already giving you a little bit of interpretation here, you can interpret the difference between the two curves in such a way that your hard process is the one with the dotted line, and if you switch on radiation, what's basically happening is that, as I've said, you reduce the hard scattering energy because photons, meaning energy, goes away before. And if you, for example, have an energy that is above resonance, you can hit the resonance before the whole process starts. You just emit an appropriate amount of energy, so that then after this energy reduction, the hard process hits the resonance, which would mean actually that if you have an energy higher than the resonance, in a way you get a large impact of this so-called initial state radiation. You get more events, because by first radiating photons, you can kind of return to the resonance peak. Clear or not so clear? I see mixed faces, let's say. What I wanted to argue for is basically what you see here. So dotted is without radiation, but with radiation you can kind of effectively go back to this energy where you have the resonance, and this means that actually the measured cross-section is higher than your, let's call it, lowest order prediction. What you see here coming up is what people call a radiative tail. These are things we will talk in more detail tomorrow. Okay, anyway, I made already the point that you can, for example, make several measurements by sweeping over the resonance. This is just the cross-section, and there's also, as I've said, various asymmetries and also ratios of decay width, where the C boson decays into hadrons or only into leptons, things like this, and you can confront them all with a prediction from the standard model. So this was done quite intensely at lab times, and one way of doing this was, for example, to introduce these quantities here. These are not exactly the couplings that I have introduced yesterday when I built up the standard model, although they look exactly the same, like V minus A, you hopefully remember. This is meant to include also all kind of higher order corrections in this vertex here. That means this is kind of introducing so-called pseudo observables that you can almost directly confront with data. So you do just a model calculation with basically lowest order with these effective couplings, and you confront it with data. And in theory, of course, you would have to take into account also all kind of corrections like loop corrections to these quantities. So just by measuring then these form factors or effective couplings, you can confront them with higher order predictions in theory. And there are actually two type of observables that you can construct out of these auxiliary quantities GA and GV. This is actually, of course, the combinations as they go into predictions. For example, in the decay width, what you basically see is G squared plus G squared, A plus H squared plus V squared. Or in the asymmetries, we basically get access to the ratio of the two. And the basic quantities ruling the asymmetries are these A factors. For example, the forward-backward asymmetry for fermion anti-fermion production goes with a product this factor for electrons and the final state fermion F. And you see, this is just sensitive to the ratio of those two. And this ratio you can then turn into something that looks like the weak mixing angle. Yeah, just using lowest order relations. Let me jump forward one slide. You can just cook up this combination here, and if you plug in the lowest order predictions for V and A or GA, GV, you get the squared of this weak mixing angle. That's the way it is understood. It's called the effective weak mixing angle because in theory, already all kind of corrections go in there. Okay, but I was kind of getting ahead of myself. Oops, sorry, wrong direction. Here we are. So what was done? It was the experimental confrontation in terms of GV and GA. And you can do it, for example, for all kind of leptons here, GA on this side and GV on this side. What you see here is the following. You see the ellipses, which were just results of the fit for electrons, muons, and taus. And you see they kind of have an overlap region here. And if you combine everything, assuming lepton universality, you get this black ellipse. So there was confirmation of lepton universality at lab already, and you can confront it with a standard model. And the standard model prediction was this kind of yellowish band here, parameterized by the Higgs boson mass, which was not yet known, and the top mass, which was also not known before 95, when the top was found. And you see that these higher order corrections already gave you information about the allowed ranges of MT and MH, which means that higher order corrections are just a window beyond the energy reach of your collider, because all the particles of the model enter already the radiative corrections. So this was basically the one major result of electric position physics at the time. And the success was not only to show agreement between a standard model for various or for certain MT, MH values, but also the fact that you could reach this agreement basically only by including these higher order effects. Which means higher order effects, these are really corrections that come at the quantum level. So in a way, you test your theory as a quantum field theory. So this was what GV and GH. If you take the ratio of the two, the constraint coming from a standard model is even tighter. And the result of that you see here. You see here on the horizontal line the value of this effective weak mixing angle. And that means that you just can line up the measurements here from various asymmetries here. For example, AFB 0L means it's a forward-backward asymmetry for lepton pair production. There is, for example, also here AFB for B. This means this is the value for BB bar production. And you see they were not so nicely compatible with each other. It's not really a disaster that we have, for example, measurements that are not fully compatible. There will always be tensions at the 1 to 3 sigma level if you have several measurements. But still, that was something to think about, in particular because not at lab, but at SLC, that means at the linear collider in SLAC, there was also a version of this asymmetry measured, namely a polarization asymmetry, which you can also translate into information about this effective weak mixing angle. And this value and the one from a B quarks, they are the most precise single measurements. And they are away from each other by something like 2.5 to 3 sigma. Now, actually, they should be the same if everything works as we think in theory, but they are a little bit apart. By the way, historically, they were even further apart. And then people refined their analysis and thought about various things. So they moved closer to each other, which is, of course, something that sounds a bit fishy. If you have measurements and they just know where to go, and in the next round they come closer, it's a bit strange. It's kind of a little bit of a central value bias, but what can you do? Psychology is still in the game. You just have to take it with a grain of salt. What stayed, of course, was the difference in terms of 3 sigma, because the precision increased. So the error bars shrunk and they just moved a bit closer, but it was always something like a 3 sigma difference. It's not yet resolved why this is the case. maybe fluctuations or whatever, underestimate uncertainties, I don't know. It will be nice to see what the LHC has to say to this, because the eventual precision for the corresponding measurement at the LHC will also be quite high, and it's coming up, and well, at the moment it's not yet clear what is favored. It's nicely in line with those measurements, and we will see. So the reason already at that time why this was so important, you can see here, yeah, this band that goes off at the diagonal is the standard model prediction, and this depends on the Higgs boson mass. This was already later when the top was discovered. Yeah, at least here you see a top mass from early measurements, and so you see that the standard model kind of intersected with this yellow band coming from experiment, which means that the standard model prediction was only in line with measurements which were getting more and more precise for a certain Higgs mass window. Yeah, so you see really that the first indirect constraints on the Higgs boson mass came up at lab, although the Higgs boson was not yet in sight. Okay, so this was C boson precision physics at lab and SLC. Let's move on to lab 2, W pairs. Here it can be a bit quicker. As said, there's of course cross-section measurements, the W boson mass measurements, and couplings analysis. Let's look a little bit into this. The cross-section here is of course much more complicated to calculate, because all of a sudden it's a 2 to 4 process with 2 resonances in there, not only one with 2 final state particles. So in theory, we had a much harder time. Oh, the rain vanished, yeah, because this was kind of an opportunity to also draw attention to the fact that the rain and myself, we also worked on this, and we had kind of fun and also pain to suffer at that time. So on the experimental side, beautiful new type of events came in, like for example, for jet production, where the 2 W bosons decay each into a jet pair, and the experimentalists did a great job in analyzing all this kind of for Fermi final states. Just to show you one picture here from Aleph, you see nicely separated jet activities in the detector. And finally, the cross-section confrontation between theory and experiment looked like this. Let's first look on the left-hand side. Over the energy, you see just the cross-section prediction. And in the early days, actually, people just talked about standard model and made lousy lowest order predictions until they realized that we should do a bit better. But already early on, you see here, you see differences in prediction if you just play around at the qualitative level with these non-abelian couplings, gamma WW and ZWW. For example, if you switch off the ZWW vertex, yeah, you get, as I've said, you get a cross-section which runs crazy, yeah, in terms of bad high energy behavior, and you see it already upcoming here. Let's take the dashed line here. You see the standard model cross-section follows this green band, but without this vertex in lowest order, you see already the trouble coming up here. Yeah, the cross-section does not go down sufficiently fast to produce something unitary. If you have, for example, no new neutrino exchange, you have this dotted line. So you really need the full standard model prediction in lowest order to get the shape more or less right. And the final measurements here that were done were already at the level of very few percent. There was one particularly precise point, which is here, that was at 189 GeV or so, where people started to realize, our lowest order predictions and the little bit of improvement we have done with the initial state radiation is not enough. So that's where our calculations set in. The result you see here, a much smaller band, which reflects theory uncertainties. And here in this kind of inset, you see there is nice agreement between theory and experiment. Yeah, so this nice agreement already put lab experimentalists in the situation that they could go in more detail into couplings analysis, which is kind of shown here. So what people did, just in some phenomenological ansatz, they parameterized deviations from the standard model prediction in this triple gauge boson vertex by introducing 3 parameters, which are indicated here at the Lagrangian level. So this G here and the kappa, they look a bit like standard model structures. And by setting them to certain values, which are indicated here, for example, you also find the standard model prediction, but by letting them, for example, deviate from the standard model values, which are normalized to 1 for G and kappa, you could kind of constrain deviations from the standard model. And yet another operator was included here. And together these three type of operators for the set and for the photon, they are enough actually to fully parameterize all possible deviations from tensor structures as predicted by the standard model. So to make it really tractable, this makes in total 6 parameters. People played a little bit with constraints, for example, to cook everything down to 3 parameters. Again, this means here deriving everything from a gauge invariant model where this W plus minus fields together with this linear combination furnishing the photon and the set was taken as a W triplet. This gives you the constraint again that you have basically 3 fields, and this led to this constraint, which makes it better to address experimentally. So what came out of it was this, the G here, the lambda for the photon, and here we have the kappa for the photon. They were just fitted together, and you see the allowed ranges indicated here at various confidence levels in red and yellow. They all have in common that the standard model prediction, which is 0, 1 here, 1, 1 here, and 1, 0 there. The standard model prediction is always in there, which means really that this analysis nicely confirmed the non-abelian gauge boson self-interactions at the level of very few percent. So this was yet another qualitative step in establishing really the dynamics of the standard model. So the global status before Higgs discovery is visualized here in this cartoon. You see again here these asymmetries and the W boson mass from muon decay over a range in Higgs boson mass. The error bars are just measurements, and the greenish band here visualizes the still allowed range in the Higgs boson mass when you fit theory to data. And the selection of these observables are just those observables that have the highest sensitivity to the Higgs boson mass dependence. So you see that basically everything fit together quite nicely. There is this kind of a little bit of an outlier for this AFB, which I have already discussed. You can also look into more precision measurements like these R ratios, again, asymmetries, and many things that you might recognize here. And you can take the result of the fit and compare it with the experimental value, and you see that the deviations at this, you see in this axis, it's called the pull or so, is that typically there is agreement within at most 2 sigma. So, the largest outlier is this AFB here. So you can really call it good agreement between standard model and measurements, and this was done over and over before 2012, in particular to constrain the Higgs boson mass. The result you see here, the major sensitivity comes from such subdiagrams, and in 97 here you saw that the yellow region was excluded by the direct search for the Higgs at lab, and this blue band had a minimum in this chi-squared fit between 100 and 200 GeV for the Higgs boson mass. For this reason, it's also called the blue band plot. So if you just follow now the history in time, you see that, of course, the excluded region went up until 114 GeV at lab times, and the width of this blue band became more and more narrow. It flips a little bit back and forth because data changed a bit and also theory pieces were added. But you see that also the axis changed here, and in a way, the blue band singled out the region around 100 GeV for the Higgs boson mass, which is not so bad. And at some point, you see that Tevatron kicks in by excluding a window in the Higgs mass around 2 MW, because they had the highest cross section for Higgs production there. Yeah, but they didn't see it, so they could exclude a range, and so it went on. Yeah, the excluded region also increased a bit until finally, shortly before the status winter 2012. That's not true. It's March. It must be. I have to change this because in winter it was the Higgs boson was already found. Okay, forget about this. I will change that. It was March 2012. You see that the confrontation tightened a lot until only this small window was not yet excluded. And of course, we know that the Higgs boson exactly showed up there. Yeah, so this was really a masterpiece from many people working together to get this piece of precision physics really done in a very consistent way. So where does this leave us? It leaves us with a lot of delay on the clock and with this situation. The status of the standard model after 2012 was as follows. The standard model particle content with the discovery of the Higgs boson was experimentally completely established, but even more, the collider data showed very good agreement between standard model predictions and really confirmed the standard model as quantum field theory. I think one cannot overemphasize this point. And as part of this confrontation between theory and experiment, looking back at the time, it was really a major triumph of electroweak precision physics to be able to constrain the masses of the not yet discovered particles, the top quark and Higgs boson, before their discovery in such a way that experimentally really one was able to exploit this and to refine the search in this direction. So this is actually the end of the first lecture, and what's still going to come is more on the theory background concerning higher order calculations in electroweak theory, which played a major role in this development, as already emphasized. I will in particular highlight features of electroweak corrections, which are not so much actually common in QCD, for example. And finally, in the last lecture, I will guide you a little bit through electroweak phenomenology at the LHC. Is there any questions up to this point? You're in my lecture, you're quite silent. Come up with questions. I am happy to answer them and take them also in between. So I have to take care of the Zoom session as well. So I should stop this here. What else? Lecture number 2. And I have to share the slides again. Okay, should have worked. Hope so, at least. And as promised, we now go to prepare the ground to calculate higher order corrections, and electroweak renormalization is an important ingredient in this. So you heard already a little bit about renormalization. So part of the stuff I will present to you was already explained. Maybe I repeat it in different words. If it is too basic, you can also tell me, of course. So the plan is to guide you a little bit through the structure of loop corrections and to introduce the concept of renormalization before I apply it really to the electroweak sector of the standard model, and I will stick to the next to leading order level. If I have time at the end, which is not very likely, I could also tell you more about, for example, charge renormalization to all orders. Yeah, basically because I think I developed a new idea 2 years ago or so and wrote a paper which I find quite nice, and the idea is easy to grasp. So if I don't make it to that point, if you just look into the slides, I think you can get the idea. Most likely I have to drop part 3 here. So let's start with part 1. And the plan in higher order calculations is the following. You first formulate your theory in terms of a Lagrangian, and you go through quantization to make it really available for perturbative evaluations. This is basically where we ended the last lecture. In order to do these higher order calculations, you first need the Feynman rules. You have to draw Feynman graphs for your favorite process. And if you go to higher orders, you have to deal with loop integrals, actually also with emission corrections like Bremsstrahlung. And what you find is that you have divergences, which already popped up also already on the blackboard in other lectures. And that means if you have divergences, you first have to find a way to handle them. You have to map them to something finite to be able to do consistent calculations. You cannot just shuffle around divergent expressions and cancel them wildly. This will not work. You really have to embed your theory into a framework where the divergences are something finite at the basis of the whole theory. So this step is called regularization. And when you have accomplished this, everything is nominally finite, but it's not yet a theory which you ultimately aim at, because you have kind of changed the theory, modified it to make divergent things finite. And before you go back to your original theory, you have to reparameterize the theory in such a way that in this step of going back to your original theory, the predictions for observables become finite expressions. This is the issue in renormalization, which eliminates ultraviolet divergence, at least in theories which are called renormalizable. So this general program is, of course, full of technical problems. I will not mention them all, but part of them. But what you finally do is you predict, of course, observables like cross sections, decay width. Some of them actually are called pseudo observables because they are something in between. They are result from let's say a fit of an effective model to data, and in the effective model you can calculate the basic parameters like this effective mixing angle. These are called pseudo observables. But there's a long way to go there. In particular, it's full of technical problems, for example, also like infrared divergences, and you have to define those observables and pseudo observables in such a way that you can really predict them in a sound way. Lenz has, for example, mentioned already infrared safety of QZD prediction. So these are things that come in addition, in this whole plan to calculate observables. So before I go into detail concerning these higher order corrections, I still want to prepare the ground a bit what kind of observables we calculate in theory. So I have to make a catalog of different objects that we meet. And in principle, I could start here with S matrix elements and amplitudes, because if you square them, you directly have basically probabilities or probability densities. But if you really do it field theoretically in a sound way, you introduce additional objects to really learn how to treat all these difficulties that come up, in particular these infinities. So the point is that we don't go immediately to these S matrix elements, scattering amplitudes. We define objects that contain all the information about this, and these are green functions. So actually, you're theorists, and I hope you have already met them in several places as green functions. So I just will make a catalog together with corresponding comments. So the basic definition is like this here. A green function is basically the vacuum expectation value of a time-ordered product of field operators. If you have only two of the fields, this is a propagator, a green function that solves an equation of motion, or is used to solve an equation of motion for a field. And this is just a little bit more general, that you have more field operators, not only two in there. And time ordering is really what is at the heart of time evolution in quantum field theory. So these are really the central objects in quantum field theory, and you can Yeah, if you're a bit bold about the mathematics, you can derive an expression for them in terms of a functional, or loosely speaking, a path integral, yeah, over the phase vector driven by the action of your theory. Yeah, so this is basically the way how we construct it, and we do perturbative expansions, yeah, for this functional integral. This is just a closed mathematical framework to handle things in a very general way. We don't calculate one amplitude after the other and look for divergences. This is the way to do it basically in one abstract framework, once and for all the processes with the same machinery. Yeah, that is one of the strengths of this green function business when directly taken them from the functional integral. Yeah, as I've said, we do it in terms of a perturbative expansion via Feynman diagrams. So if you calculate these objects, this means you calculate the following. For each of the field points x1 to xn, you have an external point. And then you just construct all the graphs where you can kind of link the points with one another by lines, which are propagators, and the vertices are just this interaction vertices. And you get structures like this, yeah, tree level stuff here and with one loop there, and this goes to infinite loop order. And you see here in this very general definition, you have plenty of graphs which are not even connected. For example, the first one or this one, which means if you go to momentum space, this means the momentum flows from here to there and here to there, but there is no momentum exchange, for example, between these 2 points here. And if you use them to calculate scattering amplitudes, this means, for example, here that these 2 points correspond to incoming fields and the other 2 points are the outgoing fields or states for the particles. And this means here that this is not really a scattering. That means the momentum just flows through. So those graphs which are not connected, they will not contribute to your scattering matrix element if you aim at calculating cross sections for scattering. This leads to the next definition. Yeah, we kind of single out only the connected graphs because we only need them for scattering processes. They are called connected green functions. And you can define them by functional relation or simply by the selection of diagrams here. Going from here to there, you just cross out all the parts here which have no connection, and you end up with this selection of diagrams. Okay, seems quite plausible. If you are finally interested in scattering matrix elements, you have to find a way how to get the S matrix or scattering amplitude out of a green function. Okay, this is a process that deserves mathematics. Yeah, that people in the 60s, our ancestors in field theory, they did a very good job there, and they also did this kind of classification. So what they cooked up, for example, is this process what we call LSZ reduction. Lehmann, Semanzik, Zimmermann were the big guys there. And what they kind of worked out is that if you take these connected graphs and you just strip away the external propagators, these are the ones that go to the external field points, then you're almost there. Yeah, you just have to associate then the lines which have no propagator anymore. You have to associate them with external states. That means you set the momenta on their mass shell, k squared is m squared, and you contract them with so-called wave functions like the Dirac spinors, UU bar, VV bar, you all know that, and polarization vectors for the vector particles. This is LSZ reduction. It brings us from these cross sections, from these connected green functions to transition amplitudes S matrix elements. This is almost the same. The step in between, I skipped this in a way in my terminology, are so-called amputated green functions, which I described already in words. What I did here, I just stripped away the external propagators. It's just an operation between green functions. External propagators and propagator corrections are gone, and I don't write a field point there because I dropped it. Still in momentum space, momentum is coming in and going out. So, and the next step, as I said, in this LSZ reduction is this on-shell procedure and the contraction with wave functions. There's one additional point one has to respect. If you have these loop diagrams in the game, you also have to repair a little bit the fact that these external loop corrections that I have stripped away, they still do something. Namely, they change the normalization of your field. You can repair this by introducing this kind of wave function renormalization factors. I called it R factors here. This is just an effect to restore the lost normalization of your fields. It's not really physics going in there. It's like in non-relativistic quantum mechanics, if you do perturbation theory, you also see that you sometimes all of a sudden, if you switch on perturbations, you start with a normalized state and you get corrections to the state. And these corrections destroy the normalization, which is not one anymore. You have to repair it. These are these R factors. Okay, part of the game in LSZ reduction. If you have done all this, you have your amplitudes, and the amplitudes you have to square, and in most cases to integrate over Lorentz invariant phase space to get an observable, for example, cross section. So this is the field theoretical way to go there. So why do we do it in this complicated way? With the green functions, because in particular, because of this business with the divergences. They are most easily handled if you have a proper classification of your field theoretical background. For example, the idea now is that if you, let me go back, if you have this kind of subgraphs, for example, here a loop in there, but still something else, which is only connected to the rest with some tree level structure. And also here, it is clear that it is a good idea to bring everything under control inside this core of the diagram, which contains a loop, because the loop is the troublemaker, not this part below here. So it's a good idea to concentrate on this really irreducible loop part. And this leads us to yet another type of green functions, which are called vertex functions. These are just the irreducible building blocks in the loops. One reason to single them out is exactly to control the divergences. And the second reason is that if you have calculated all these blocks with a loop, you can just dress them with a little bit of tree level structures to make them full diagrams contributing in your calculation. And often you have this kind of loop structures like indicated here already in several places, and you have to calculate only once and for all. And it is modern machinery of amplitude generators with recursive methods. Very often it is exploited that you have one and the same building block appearing in several places. So it's just to further structure your calculation and also to profit from it in practical calculations. So let's look into these vertex functions also a little bit. The easiest way is, for example, to have just a loop-like structure, like here indicated in this gray block, and only one external leg. It's a bit unusual. In momentum space, it's also clear that the momentum flowing here must be zero because nothing goes out or in anymore once you have just fixed the momentum at this one line. Diagrams like this don't play a role in QCD at all. Because they turn out to be zero for reasons I maybe explain you later. But in electroweak theory, things like this are there. They are very often ignored when you just have a beginner's course on calculations, including also higher orders. But they are there, and they are called tadpoles inside our community. Okay, I'm late, but a 30-minute anecdote is worth it. They look so super easy and simple. And when they first introduced, don't ask me who was that. I don't know. Maybe Doreen knows. When they were introduced you're already smiling. You know the story, maybe. It was just introducing the name tadpoles in a paper. I don't know who it was. So, but the law is that the referee told the author, look, tadpole is not a physics terminology, change it. There are things like fermions, bosons, I don't know what. So make it sound a bit more physical, like a particle. So In the revised version, the author proposed then, let's call it a spermion for obvious reasons. And then the referee just switched back, said, no, we stick with tadpoles. So, okay, anyway. I heard it from several directions, but nobody told me who was the author. Sorry? It was Coleman? You see, he's confirming the story. Okay, cool. Maybe I heard it and forgot about it. Okay. Yeah, must be one of the cool Americans, of course. So, tadpoles. In electroweak theory, when you start calculations, they are not zero. It's easy to force them to be zero in lowest order, where there is no loop at all here, which is just going to the minimum of the Higgs potential, yeah, which is killing in the Lagrangian by a proper normalization of your fields. It's killing the linear term in the Higgs boson. This is basically the essence of this type of graphs here. They correspond to linear terms in the Lagrangian, but if you switch on higher orders, you get such terms. Okay, let me go to my own comments here. I told you that in QCD, nothing like this is there. This has the reason because you can only expect those graphs to produce something non-zero if the line here corresponds to a field that carries the quantum numbers of the vacuum. And there is nothing like this in QCD. There are quarks and gluons. They all have spin. Vacuum has no spin. But the Higgs boson is such a candidate. In lowest order, it's easy to achieve this, as I've said, go to the minimum of Higgs potential. In higher orders, you have to repair this in a way. If you don't do it, I assume it is done below. If you don't do it, you have a little bit of trouble when you define a propagator, because what was a propagator? Let's take this subgraph here. Yeah, this looks like a correction to a propagator. And if you have these tadpoles around, you can also think, for example, I have a blackboard. You also have things like this, which look like a correction to a propagator. Yeah? And if you have things like this not eliminated in this or another way, you get all these kind of graphs contributing to propagators. In particular, it destroys a relation between so-called two-point vertex functions, or simply two-point functions, and propagators as indicated here, or better, skip this, as indicated there. This is just our full propagator, the G. Yeah? So if you start to calculate it, you know you have a free propagator, you have loop insertions, you have more loop insertions. And the black blob here is just what we call a one-particle irreducible subgraph, which means if you cut one line, the graph does not split into two graphs. So, for example, this thing here, this is one particle irreducible called 1pi. Because if I cut not the external ones, but if I cut an internal line, it's still connected. What is not one particle irreducible is, for example, something like that, like this unpleasant tadpole, because if I cut this, you disconnect two pieces of the graph. So this is not one particle irreducible. And for the whole machinery to work properly, it's good to eliminate these structures, because then your propagator just receives corrections of this kind, yeah, but not of this kind. Okay, maybe it's a bit too detailed at this level, but I just want to draw your attention to points that are a little bit off in electroweak theory, when you just come from QED or QCD. Okay, I just wanted to introduce here these vertex functions as the true building blocks of all kind of graphs. You have this one-point function, the tadpole, you have two-point functions, which are the propagators, and this means these blobs here, or this loop-induced blob, they furnish your propagator just by iterating all these insertions. You can sum them up, because you just have one and the same irreducible block here appearing all over the place. So you see, actually, when I write this part here, there's no double counting involved, because by definition, this is one particle irreducible, but this is reducible because I can cut this line here. That means this structure is not yet contained in here. And if you iterate this, you get a geometric series, you can sum it up. And your whole propagator here looks like this, where you have the structure like in lowest order, plus this insertion now in the numerator, in the denominator. And if you remember already, I had already a little bit of trouble with resonances, where p squared is m squared actually led to something infinity. You see there's a chance that this is not leading to a pole, because you have, by resummation of these blobs here, you have introduced something in the denominator, which is actually really our way to describe resonances, the resummation of these blobs. So these irreducible blobs play really a major role in the whole business. Okay, and the inverse of this green function turns out to be exactly this 2-point green function, which is just free part, the p squared minus m squared plus this loop induced part. Actually, I still have to change something in my normalization. There's an I missing here. Okay, I will repair this. So this relation between reducible and irreducible blobs carries over to all kinds of green functions, the so-called endpoint functions. And the rule is, just giving you this graphical example, that the full amputated green function, so this is almost the amplitude, can be decomposed into something that is fully irreducible, plus these structures where you combine all these internal blobs in a proper way. For example, corrections to this vertex, including also lowest order predictions, and propagators which are of this resummed kind here. So you see, what we are after are these amplitudes, and you can nicely construct them by combining all these inner blobs in a reasonable way. And so what we have to do in order, when we do calculations and control infinities, we just have to control everything for this gray blobs, which are the one particle irreducible pieces to these amplitudes actually. And these are also the objects that were subject in these renormalization proofs done by various people, in particular by Toft. So this was just the prelude. Now we come, are there any questions here? Now we come to these divergences in more detail. And I think I can be brief here because they were already discussed earlier in lectures. So where do they show up? For example, in these loop integrals, and there are ultraviolet divergences, which are divergences that build up when at least one component of a loop momentum, which is integrated over in a loop diagram, runs to infinity, as for example here, or the infrared divergences, they can pop up if the loop momentum approaches a certain value. So actually these divergences can be found out very easily by what we call power counting. These are all 4 vectors and squared 4 vectors and stuff, but for identifying at least that one loop, for identifying divergences, you can almost treat them like normal variables. Okay, let me skip this because it's kind of hand waving stuff. If you do really the full calculation, you see why this is the case. Basically, if you go to spherical coordinates, this may basically the length of those vectors that plays a role. So here, for example, that means if we just treat Q as like a normal integration variable, any component of this, then you see if q becomes large, I have something like q to power 4 in the denominator, and d for q, which is something like q to power 3 times dq. It conspires together to something that looks for large q values like dq over q, and if q goes to infinity, this diverges at the upper end of the integral, logarithmically, because the integral is just a log of q. So that's a logarithmic ultraviolet divergence that is expected for this integral, and exactly that happens in the calculation. Infrared divergence, for example, you can see in this kind of integral here, which looks, by the way, still have space here, like a diagram of this kind here. I have basically some integration momentum q here. Maybe some P1 goes in there and some P2 goes out there. Then I have Q plus P1, Q plus P2 here. And the P squared here, P1 squared, is equal to the mass squared from in here, and likewise for the lower leg. So what you get is just this integral. Now you have no mass in here because there's no m squared in there. So this is a massless propagator exchanged between two external states, photon exchange, for example, or gluon. And when I now go to the region of this integral where q is very small, q goes to 0, that means the q0 here is 0, then I see the leading part of this propagator, for example, just comes with 1 power of q, the same here. So I have 1 over q squared here, which means, again, if I count now the powers for q going to 0, the leading term goes with 1 over q to power 4, again, d for q in the numerator in the integration measure. So this leaves us with a dq over q for q going to 0. Again, a log is the integral, and you get a log of 0. Again, a logarithmic divergence, but now it's called a soft divergence here. There are also collinear divergences. I will not talk about this at this point. So, as said, we need the process of regularization. We have to extend the theory in any appropriate way by a free parameter which is not yet there. Because we can then, if we do it in a clever way, achieve that for any finite value, let's say, or any region for this new parameter, we can tune the extension in such a way that I get finite integrals. And when I go back to any value, I called it here delta 0, then I get back my original theory and the integrals diverge. Which means that I have something, for example, when I tune everything that the delta 0 is 0, I could have a log of delta. So for log delta is fine as long as delta is not 0. But when delta approaches 0, I get a logarithmic divergences, which could be actually the case here. So, as said, this is not the full solution to the problem. It's just our intermediate step to do the calculation, because if you go back to our original theory for any kind of thing called xi that you have calculated, the limit maybe does not exist. And the trick is, of course, then, before we do that, we split this observable parameter quantity, whatever it is, into pieces. One that approaches a value that makes sense, plus the rest that contains the infinity. And we have to shift this infinite part to some place where it doesn't matter for physics anymore. And this is the step of renormalization. We need a reparametrization of the theory in such a way that I get relations between different quantities that are measurable, that are finite. Okay, I come to this hopefully soon. So, regularization still is our main theme. What we do is dimensional regularization, because it's so easy if you know what to do, and it preserves in particular also our gauge invariant structure of the theory. And you can use it to regularize ultraviolet and infrared divergences, as I said, in a gauge invariant way, and it's easy to use. So what we basically do is when we have these integrals over loop momenta d4q, we interpret this as an integral over not a four-dimensional, but over a d-dimensional momentum. And well, to keep actually the mass dimension of the integrals to be the canonical value, for example, for this d4q, it should be 4. Yeah, we introduce a prefactor with the power 4 minus d. So this approaches 1 when d goes to 4. Yeah, and mu is a reference mass scale without any physical meaning at this moment. And then by choosing d either larger or smaller than 4, the integral might converge. Actually, it does at some point. The problem is that it's not yet good enough to have, let's say, positive integer values for d, which might help to make an integral finite, but to have really a limiting procedure, you need a continuous range for d. And actually what we do is with a little bit of magic, we even do a continuation for this d into the complex plane. So we calculate integrals over a complex dimension. Not so easy, actually, conceptually. If you really want to know how this works, there is this nice and notorious book of John Collins called Renormalization, where he really tries everything he can to make transparent what it really means to do this complex continuation. Actually, what you do, to give you an idea, you first embed everything in an infinite dimensional space, and then the dimension of your integral is just like something like an operator on this infinite dimensional space. So it's not just counting components as we naively do it. For our perception, often it's good enough to think about multiple components, but actually d is something complex. It does work because finally the d will only show up when we do integrals in polar coordinates in the measure of the integral. So it's something nice, but it needs a little bit of making your own peace with this step. So what we do when d is complex, what is very handy is to say what is actually regularizing the integrals is the difference to 4. So what we actually often do is we write d as 4 plus or minus something small. And the standard notation, meanwhile, is to take d is 4 minus 2 epsilon. And the epsilon is exactly the one that Lenz-Dixon has used here. So epsilon to 0 brings us back to the theory. And the way the divergences show up in these integrations here are as 1 over epsilon poles. And at one loop, it's just a pole of order 1 for the ultraviolet divergences. Very often, I just combine it with some universal constants showing up, in particular from this prefactor and from other stuff. There is this Euler constant typically going together with a 1 over epsilon and a log of 4 pi, which comes from here. And I will call this in the following as a standard ultraviolet divergence called capital delta. It's just the 1 over epsilon plus a little bit of a constant. In electroweak theory, in principle, one can live with that, but it is often very convenient to use also a second type of regularization, namely mass regularization. And these infrared divergences, regularize infrared divergences. These infrared divergences have 2 different sources, and I guess Lenz also discussed this. They are so-called soft divergences and collinear divergences. What I had here with, let's say, a photon exchange between, for example, electron lines, this was a soft divergence. Where, for example, in the 1 over q squared, when this is a photon, the q goes to 0. And in principle, one can regularize these soft divergences just by giving a mass to the photon, like here. And then when q goes to 0, and I do a little bit trick with analytics, actually the m gamma squared, which is something like a photon mass, will regularize this divergence and will lead to log of m gamma. And gamma is a very small parameter, nominally infinitesimally small, an infinitesimally small photon mass, which can be used to regularize such infrared divergences. This is the standard way, the first QED higher order calculations were done. So it looks to some people some kind of old-fashioned. There's nothing fishy with it in QED. It really works, but it never really was used for gluons, for example, because the infrared structure of QCD is really a bit more complicated than in QED because of gluonic self-interactions. There it doesn't work. You can make things like this work, but it's incredibly complicated, and it's much better to use dimensional regularization. If you do this photon mass regularization for soft singularities, there's also connection to DIMREC. Basically, the log of m gamma is in 1-to-1 corresponds with such a factor of 1/epsilon. So it's not true that this is kind of old-fashioned and nobody uses it. It's in a way it's just rewriting the 1/epsilon for the soft divergences. So it's okay. The so-called collinear divergences, which, for example, also come up if I have, let's say, an electron here, photon there, and anything there. If the photon here in the loop integral becomes collinear to the electron, and the electron mass is small against the big momentum, for example, coming in here, then you also get a divergence. I have not discussed them analytically. It's also logarithmic in this electron mass. And the point is, this can be something physical, like this initial state radiation, which I showed you the effect of it earlier, because the electron mass is really a properly defined physics parameter, and it is often very smaller, very much smaller than the typical energies. So it will show up. So these kind of collinear divergences, they are sometimes really physical corrections. The log of the electron mass, for example, or muon mass, whatever, is small. So it would not make sense to blindly set the mass to 0 because it's small against any other scale, because then you end up with a divergence and you're done. You cannot get rid of it normally so easily. So sometimes these small masses that regularize collinear divergences have a physical origin. And this is the reason why this mass regularization in electroweak theory, it has a reason to be there, right? It's sometimes really physics that you have to discuss with it. So nevertheless, still, for example, the electron mass is negligible over the W boson mass in any process that lives at the scale of the W boson mass. So it makes sense to calculate, for example, your whole amplitude, the whole cross section or whatever, in the limit where the electron mass is 0, and you keep the electron mass only in pieces where it regularizes the divergence, and this typically leads to calculations which are done in the massless limit for electrons, for example, but still, whenever the mass here of the electron or any other light ferment shows up in logs where it would be infinity, there you keep it. And this procedure, is called then just mass regularization, but it is not exactly at the heart of regularizing unphysical divergences. They also can be physical, but this is the reason why this is very often done in electroweak physics. Just one comment at this point: you can also do this for quarks, of course, in principle, but whenever a quark mass logarithm survives here, it is a signal that something non-perturbative is going on. So you have to redefine your observable in such a way that this does not happen. That's the reason why infrared divergences in QCD are always taken care of with dimensional regularization. Because you have to cancel this kind of infrared divergences properly to get something physical. And then you need not do it with quark mass, you can also do it already with DIMREC, which is easier. Okay. Still no questions. Too easy or not understandable, interrupt me when appropriate. So, sorry. Yeah, let's go a little bit to the integrals. I can really be brief here because Lance told you already a lot about it. You see at the one loop level, for example, here, a 2-point integral, a 3-point integral, you just have here 2 propagators in the denominator. Here there are 3 and so on. It goes on, of course, to any kind of, let's say, higher level in the number of propagators. And in the numerator from Feynman rules, for example, for vertices like triple gauge fusion vertices whatsoever, also propagators, you might have this integration momentum showing up there as well. So what you eventually have to calculate are so-called scalar and tensor integrals. Yeah, and it is terminology that was introduced by Toft and Feldman in 79 or so, that one calls the 2-point integrals B, 3-point integrals are C, and so it goes on with D and also higher versions of it. And you have to calculate them all. At one loop, it's all doable, it's all done. But the more internal masses you have, which is not so easily happening in QCD, the more painful it becomes. Yeah? Still, you can do them all. And what these 2-point functions are delivering is something that involves, of course, the divergences, this delta here, plus finite pieces. And the finite pieces, they contain just logarithms, yeah, of unpleasant square roots and stuff. Doesn't look nice, but you can easily do it. You have to work a bit harder to do it for the 3-point functions. You get also for high enough tensors, you get divergences starting from tensor rank 2 actually. And the finite pieces, they can always be expressed in terms of dilogarithmic functions, which is just an integral over log. And if you take again integrals over dilogarithmic functions, you get trilogarithmic functions and then the polylogs after n times. And so this is an important class of functions. So you can do this also for 4-point integrals, box integrals. And yeah, with many masses in there, it's really a pain to do them, but all done. You can just use libraries, for example, to make use of them in your calculations. For more than 4 external legs, you can reduce, Lance also told you that, you can reduce them algebraically to the lower ones, up to 4 external legs. This has to do with the fact that in 4-dimensional Minkowski space, you have at most 4 linearly independent external momenta. So if you add one more, automatically, this is linearly dependent from the other ones. And this is at the heart of the trick to algebraically reduce these 5, 6, and higher point functions to the integrals up to box functions. I will not go into details here. It's kind of nice mathematics. In fact, it's a bit cumbersome, but very useful. So that's just the integrals. Why does it skip? Yeah, these features of one-loop integrals, basically, I have almost explained them all. Like, for example, the appearance of these dialog functions, which are enough at one loop. And the tensor integrals, just to mention this also, they need not be calculated as integrals. You can algebraically reduce them to the scalar integrals, where you have only, like here, the 1, or here in the numerator. The standard way of doing this is Passarino-Feldman reduction, but you can also do it differently. It's just calculating these coefficients, for example, here, that are necessary to build up this vector integral here for the 2-point function, here for the 3-point function. It is clear you calculate something that itself is a vector, because everything follows covariant rules in relativity. This means that, for example, for the 2-point function, everything has to be proportional to the momentum that flows into your bubble, like here. And this coefficient here is, again, a scalar integral. And you can just algebraically get it from the original standard scalar integral with a 1 in the numerator. Okay. If you have questions to that, we can handle this offline maybe. One-loop integrals, they are all doable, they are all done. and you can take them from libraries. So at least I hope that I can complete now the idea that leads us to renormalization at the one loop level here. And I start just with let's say this kind of 2-point function business, namely, for example, here as indicated by a self energy, so corrections like this. And if you just do these integrals, you saw that this standard one loop piece is always appearing. Now you can isolate it. And what you find also in non-renormalizable theories actually is that these divergent pieces, they all go, let's say, with polynomials in the external momentum and masses. And in renormalizable theories like the standard model, this polynomial is exactly of this order as the corresponding piece from which you get it out of the Lagrangian. For example, here the 2-point functions, they go with 2 fields, and the 2 fields, they can have, either of them can have, for example, just one derivative coming with it, and the derivative momentum is a momentum factor. So we have 2 external lines, 2 momentum factors, and this is telling you that the divergent piece can at most have a p squared, no p to power 4 or so. This would deserve or require 4 derivatives. So what you get in self-energy diagrams is something that goes with p squared, something that goes with a constant called C2 here, plus something that is finite, okay? So let's look what it does if you plug in this correction into this Dyson series for the whole propagator, which I calculated to be this piece here with this sigma exactly in the denominator here. And if I just follow the divergent piece here, I see that in the vicinity of the resonance, for example, here, the leading behavior originates from a Taylor expansion around p squared is m squared. So I have, of course, to 0 order the sigma of m squared plus something that goes with a first order derivative times p squared minus m squared, and I can, in one loop approximation, I can factor that out. If you just multiply this out and keep only terms linear in sigma and sigma prime, what you have here actually reduces to the Taylor expansion of the sigma in this expression. So why am I doing this? Because I want to know in how far the pole structure of this resonance, which is telling me where the free particle would sit, in how far this is changed. And I see that the location of the pole, which originally in lowest order was p squared at the point m squared, has changed if sigma of m squared is not 0. So that means that the location of the pole is shifted by a higher order correction. But the pole location is something that we associate with the mass of the particle in its almost free propagation. So this is telling you that higher order corrections bring you away from your mass value that you have there in lowest order. Lowest order is 1 over p squared minus m squared. And corrections change it. This is not so unnatural that this happens, because who is telling you that the m squared that you write down in a Lagrangian is really the true value of your mass? Because you have made this association just by looking into tree-level stuff. And in higher order, it can change. And this is at the heart of the idea of renormalization. Then we have to consider as the mass of the particle not the original m squared, but the combination with the corrections. And here is actually how the divergences in there will get absorbed by a redefinition of the mass. This is then what we do as a normalization. Likewise, the prefactor here changes the residue on the pole. The residue here is just I. And here the residue is I over 1 over 1 plus sigma prime. And this is you can associate this with a normalization of the field that describes the propagation. And this is exactly related to this R factor, yeah, where the normalization of your state is changed. So if you repair the lost normalization of the fields, we will get rid of the divergences in there. And you see here, I get rid basically of the constant piece plus the piece here at p squared is m squared, and the p squared divergence here, that goes away with this one. So we get already idea how we get away with the divergences. This is just for the 2-point functions. For interaction vertices, it is very similar. For example, let's take a toy model with a 4-point interaction here. That means just a scalar theory with one interaction like here. I can also have higher order corrections to this vertex function. For example, something like, let me remove this one, something like this in this 4-point interaction. Yeah, you see kind of a bubble-like structure, it's infinite. And so actually, I also have here infinity is coming up there. If you do this power counting stuff, you will see it's just a constant that's an infinity. And this constant, yeah, I can absorb actually in the redefinition of this constant. Yeah, if I say, actually the lambda here is not really motivated, it's some kind of preliminary lowest order lambda there. Yeah, I have to actually take lambda from an experiment, and whatever I match to the experiment and I have higher order correction will not matching lambda itself, but lambda plus, yeah, well, a correction already. And this will kind of absorb the infinity building up there, which is this constant piece here in the redefinition of this lambda. Yeah, so higher order corrections also change coupling strengths. Oops. So let me find an appropriate point to stop here. Maybe I just recite again some statements about the structure of divergences, which I have more or less already told you in words. So there are 2 types of field theories, normalizable field theories and non-renormalizable field theories. What is the difference? I told you actually that, going back one slide, you have to worry about shifts in, let's say, propagator poles, normalization of fields, coupling strength. This will always happen independent of infinities. But for renormalizable theories, a proper redefinition of masses and couplings will absorb all the infinities. For non-renormalizable, it will not absorb all the infinities. Some will remain. Yeah, that is the big difference between renormalizable and non-renormalizable field theories. So among the renormalizable theories, there are also, again, 2 prototypes of theories. One without symmetries. Yeah, there is the statement, just again from work of the 60s, that if you have a field theory with non-negative mass dimensions, you will always be able to absorb the infinities, and then you are done. Another procedure is called BPHZ procedure. This is Bogolyubov, Parasyuk, Hepp, and again Zimmermann, as far as I remember. And that works nicely. Unfortunately, this does not immediately apply to theories with symmetries, like, for example, gauge theories. And there one really has to dig into the relations between different green functions induced by symmetries, that you can really keep upright and maintain these symmetry relations during this renormalization procedure, because you have less free parameters, seemingly less free parameters, than you would like to have to absorb all the infinities. Because of symmetry relations, you have reduced the number of input parameters. So the relations between different, let's say, green functions, turn into relations between infinities. And if you just, for example, redefine your coupling in such a way to get rid of divergences in one particular vertex, let's say a 3-point vertex, at the same time the symmetry is repairing all the rest, that also your 4-point interactions become finite. This you have to show, and this is exactly what Toft and to some extent also Feldman did, and it earned them the Nobel Prize. So this was really a major step. Non-renormalizable field theories I will not talk about. These are, for example, these theories like SMEFT, where you can still make sense out of them if you restrict the validity of the model, let's say, to a certain momentum transfer inside a certain loop order. Then you also have finitely many constants that you can redefine to absorb divergences. But you cannot push this to infinite loop order. Otherwise, you would need infinitely many free parameters. Okay, these are things you will learn from Ilaria preview. So I think I should stop here, just checking where to go. I didn't make it to the point I wanted to do, but let's take this as the entry point tomorrow. And I still have to catch up with even more delay than before. Okay, are there any questions at this point? Okay. Yeah, okay, go ahead. Yes. You should what, sorry?
But then it's not really necessary. But from the theoretical perspective, that's what I'm thinking of.
Okay, so first of all, this is a very general thing. It has nothing to do with S channel and T channel. The difference is in practice. It has different consequences. So what is S and T channel? S channel means, for example, this fusion, two incoming particles fused to something, like C production in A plus and minus, as we have seen. And the difference is that the momentum transfer, the K squared for the S channel, is positive. And this means that you can hit the pole here. So it can happen in special processes that you really hit a resonance. So this is something that you have potentially to do in S-channel production. Not everywhere, but there are processes where it really plays a role. In T-channel production, for example, let's say here I have an incoming particle, it emits something is coming from here, and let's do it vertically, and I have all kind of loop corrections here in this type of propagator. Then the difference is that the momentum, the K that comes in here it's called P. Anyway, this has the property that P squared almost everywhere in T-channel, there are exceptions at the boundary phase space, but here typically for massless situations, the P squared is negative. And this means that in T-channel exchange, you never can hit the resonance here, because if P squared is negative, P squared minus M squared is even more negative. You don't hit the zero. So in practice, it can happen that you need this resummation really also in calculations to get away with this resonance infinity in S-channel production, but in T-channel production, you don't need it. Maybe a last comment about this, and I will tell you more about this tomorrow or so. It's a dangerous thing to do this in practice, because consistency relations in higher order calculation typically work order by order. That means you do a full tree level calculation, and if you don't have a resonance, actually life is okay. If you do a one loop calculation and you just stick with one loop insertions like here, there, wherever, here, then all the one loop pieces can conspire together to really fulfill consistency relations there. But if you do things like this and include to infinite order something, let's say you resum all the one loop stuff, then you have a problem, because you have part of the two loop corrections in and another part you are missing. So you disturb consistency relations at the two loop level. So whenever you do this kind of resummation, in particular in electroweak theory, you're running into danger that you screw up things. You can screw up ultraviolet finiteness. You can screw up gauge invariance very easily, things like this. So this is always a dangerous thing. Sometimes you have to do it, but then you really have to do it with great care. Okay, I think that's enough for the moment.